Welcome to the course on how to process and extract features from sound signals. My name is Sebastián Moilner. I'm a neuroscientist from Argentina, and I employ deep learning models from my research. So the outline is the following. First, we are going to do a brief introduction to deep learning, and in particular to convolutional neural networks. Then we are going to do a pipeline for audio preprocessing. We are going to code it with Python. Then we are going to prepare a FastAI model to do audio tagging. And lastly, we are going to employ a Keras model also to do audio tagging. So what is deep learning? Well, deep learning is a field from artificial intelligence. The idea behind artificial intelligence is to make a program that can sense, reason, act, and adapt, similarly that a human will do. Machine learning is a broader field where deep learning is a subfield. And in machine learning, what you do is to try to make a program to learn from the data. It's a data-driven technique, so you don't have to code any particular rule on how to process the data. The idea is that the machine will learn directly from the data itself. And in particular, you have deep learning, which is a subset of machine learning. And the idea is to use multi-layer neural networks to do the job. So there are different algorithms that you can use for machine learning. There are some models that they are more interpretable than others. For instance, it's different to make a regression where you can select the features for the model than a convolutional neural network, where the idea is that the model itself will select the features automatically. So in the field of machine learning, you have supervised machine learning, where you need to tag the data. For instance, if I want to classify a sound from a dog and distinguish it for a sound of a cat, I will need to tag the sound, so the machine will be able, hopefully, to distinguish between them. But in a supervised learning, like when you use k-means or clustering, the idea is that you don't provide any tag, and the idea is that you will see in a low-dimensional graph the separation between the groups. And lastly, reinforcement learning is the idea that the program, for instance, if you want to control a robot, so the robot can learn from the environment, the idea is that you will use reinforcement learning, where you should provide some kind of goal to the model and try to do a more positive scoring when the robot is performing well. So what is the idea behind convolutional neural networks? These models are applied for image classification, object detection, and instance segmentation. For instance, if you want to classify between a cat and a dog, you will train a CNN by providing tagged images of cats and dogs. But you can also do localization, and you will have the specific location in the image of a cat. You can also do object detection when you mix different kind of images. and also segmentation to delineate the shape of the cat and the dog. These models are trained, and usually you need a very big database to train the models, because convolutional neural networks is not like a traditional machine learning algorithm like support vector machine, where more or less with 30 images for each class you can do a good classification. Because you have, in this case, a lot of features represented by pixels in the image, you need a lot of data to train the models. And also because a convolutional neural network has a lot of parameters. So they are available datasets like ImageNet online, where you can train your models, but also that you can use a already trained neural network on ImageNet and use it by transfer learning to classify images from another groups or another categories of images, not only animals, for instance. There is a challenge organized by ImageNet, by the developers of the database, where a lot of groups from different parts of the world compete against each other to see what is the best model in classifying the images. So you will have a lot of models. Each model will be more or less complex, represented by the number of parameters of the models, and you will have an accuracy rate on the image classification or an error rate. In this case, the error goes lower and lower each year, but the accuracy, you can have a representation where you will have an idea about the right amount of parameters, because if you use a very complex model, there is a chance for you to do an overfitting, which is adjusting the model that much to the training data that it doesn't generalize well. If you provide a testing data, you won't have a very good performance accuracy. So the performance in accuracy, or the error in this case, goes lower and lower. And a few years ago, there was a neural network called residual neural network, which is inspired in the visual cortex of the brain of the mammals, that outperform the performance of a human in image classification. So these models are very, very powerful. But what is a convolutional neural network? Well, a CNN uses spatial filters to reduce images to feature maps. So the idea is that you are going to have you can have a very high resolution picture, and you will employ different filters to reduce the images to specific features that you hope that are going to do a good classification after you train the neural network. But the advantage of these models is that the neural network itself will extract the features for you. That is the advantage of deep learning. So it is that the neural network will pick the best features to do a good classification. And if you use a lot of filters, you will have, at the end of the day, less parameters to tune. So you won't need to use a very high performance computer cluster to train your models if you do some kind of dimensionality reduction. Okay, in our course, what we are going to do is to apply this kind of models to audio files. An audio file, for instance, a dog barking, You can represent it by an audio wave. You will have the amplitude in the y-axis and the time in the x-axis, and you will have different parts of the audio file with louder parts. For instance, if the dog is barking here, you will have a louder segment than when the dog isn't doing any kind of sound. But the problem with this representation is that you don't have a good idea about the pitch of the sound. Because if you want to do some kind of tagging from different sound, the pitch which is the perceived frequency of the sound, gives you a lot of information, but you cannot directly know what is the frequency of the sound by looking at this image. So that's why you need a spectrogram. And in a spectrogram, you will have the frequencies in the y-axis and time in the x-axis, and you will be able to know what are the most contributing frequencies in this case to the sound. You can see that the low frequencies are the most important features in this time segment. So you will have a picture represented by the spectrogram, and you will be able to use a convolutional neural network in it, as you were classifying from dogs and cats, basically. Instead of looking for animals, you will be looking for specific kinds of spectrograms. So, what is a neural network? Well, the neural network is based in artificial neurons. The artificial neurons are inspired by the real biological neurons, where you have dendrites, the cell body or soma, the axon, and the axon terminals. And the flow of information will go from the dendrites to the axon terminals. In the case of the neuron, if you have a specific cell membrane potential that surpasses a threshold, the neuron will fire and it will transmit information. In the case of an artificial neural network, the mechanism is similar. You will have inputs represented by pixels of the image. You will have weights assigned to each of the inputs, and you will sum the inputs in this part of the algorithm. And if the inputs are positive in this case, if you do the summation of all the weights and the inputs and it's a positive number, then the neuron will fire. But if the sum is less than 0, the neuron won't fire. This is the very, very simplified version of a neuron, but it works very well for artificial intelligence perception. So there is an algorithm, which is the most basic of the algorithms in neural networks, which is the perceptron, that it's based on the idea of the artificial neuron, but it's trained. And to train it, you will need to compare the output of the neuron, in this case, with the expected response. For instance, if this kind of model tells me that this is a sound emitted from a dog, and it's not, you will have an error here. So if there is an error, you will need to tune the weights and hope that the next time the classification will be better. So this process is done a lot of times. You begin with random weights and then you adjust it. And there is that eventually the neuron will be trained to classify the sounds correctly. Mathematically, the idea is that you will need to find the minimum of the error for doing the, if you remember some calculus from college, there is that you will need to find the zero of the derivative of this function. Okay, but you can add perceptrons and form a multi-layer neural network. Basically, you will have units comprised by artificial neurons. You will stack them together in layers and you will train them using a similar algorithm. The idea is that you will start with random weights and eventually you will tune the neural network and hope that you have a convergence to a good classification output. Okay, there are a lot of parameters to tune in the neural network, for instance, the activation function. In the activation function, you can have a stepwise function for, like in the example that we seen a few slides ago, or you can have a smoother function like a sigmoid, hyperbolic tangent, and so on. The idea, if you want to do an image classification, for instance, if you want to know who is this person, is that you are going to train a convolutional neural network, which are the best model for image classification, and on each layer you will have a different level of abstraction. You will begin with the raw image as the input, and you will have higher and higher levels of abstraction when you go through the different layers of the neural network. And in the output, you will have, for instance, different names. The idea is that this person is identified just by looking at this picture. This is an example based on handwritten recognition, where you will have as an input handwritten numbers in this case, and the idea is that you will train the neural network to give you the correct response. For instance, if you put a 7 here, the idea is that you will have a 7 as the output. But things are not so easy. You will need to train this neural network a lot of times to have a good result. Okay, what is convolution? Well, convolution is the main feature or the main function of a CNN, a convolutional neural network. The idea is that you will pass a kernel. This is a kernel, is a smaller matrix that you pass through your image, and you will multiply each of the entries of this matrix by a number, sum all together, and put the input here in a smaller matrix. So for instance, you will do 1 times 1 and so on, adding all the numbers, and you will put here the result. The idea is that you will have an output with lower dimensionality than the input. One important parameter of the convolution is the stride, which is how many steps do you take for going through your input image. So if the stride is 1, it means that you will do one step at a time. In this case, the stride is 2. So if the stride is higher, you will have a shorter image, a smaller matrix. And with padding, you will deal on what to do with the borders of the image. So if you are passing a kernel through your input image, you can set the borders here as 0. So you will pass your kernel, and you will, when you're doing the multiplication of the convolution, you will put a 0 as a result of the multiplication, because this will be 0. But you can use another kind of padding, like it's padding, which is around the input with values of the edge. For instance, you can repeat this value in the edge. So depending of the padding and the stride, you will have an output matrix, which can be smaller or bigger depending of your parameters. Another kind of layer is the pooling layer, which is also to do dimensionality reduction, but in this case you will apply an operation. For instance, if you are passing through a kernel here and you do max pooling, you will look for the highest number in those segments of the matrix. So if you pass the kernel here, you will see that the highest number is 3, so you will put here 3 as the output. You can also do average pooling, where you will do, instead of looking at the maximum number, you will take the mean of all the entries of the matrix. Okay, but what is the difference with traditional machine learning? Well, in traditional machine learning, you will need to select the features by hand. For instance, if I am doing a classification by tagging some audio files, I can take as an input feature the frequency at a specific segment in time. If I guess that that will be a good feature, but the problem can be very complex, because you can build a lot of features, and if you build like thousands and thousands of features, you may end up with a very complex model that it may overfit your training data. The difference with deep learning is that deep learning takes feature engineering automatically, so you don't have to care about feature extraction yourself. You just use the neural network to pick the best features. But the problem with these models is that these models are not so interpretable like random forest classifier, for instance, where you can see what is the most important feature. You can have a feature importance analysis if you use a random forest in traditional machine learning. So each algorithm has its pros and cons. So depending on the problem, if you are doing an image classification, it's better to use deep learning. But if you are using structured data like a table, you will use traditional machine learning. Another difference between traditional machine learning and deep learning is the amount of data that you need to do a good classification. If you want to increase the performance and you are using traditional machine learning, there is a plateau here in which you may add a lot of data and you will have the same result. But in deep learning, generally you can increase the performance by adding more data. Another thing to take into account when you're dealing with the dataset is that you have a well-balanced dataset. Because if you have a highly imbalanced dataset, for instance, if you have like the positive class, for instance, if let's say that you want to classify the bark of a dog on or by recording an environment, a city sound, for instance. You will have, if there aren't so many dogs around, you will have not so many cases of dogs barking in the city. So you will have a lot of examples of sounds without any dog barkings in it. So the idea is that you will need to do an oversample or an undersampling to avoid the model to just take into account some features that they are not representative for the whole sample. For instance, if there are not so many dogs around, the model will guess that there are not so many dogs and it will give you prediction more that will be more that will give you, for instance, a lot of outputs without telling you that there are not so many dogs around. So that's why you will need to make a balanced data set so the model doesn't get any bias. Okay, regarding the bias, you will have a problem in underfitting or overfitting depending on some conditions that you may encounter by training your data. So the idea is that you will have to check if the model is not classifying very well on your weights. You will need to train the model again, change the normalization technique that you are using, check the activations because there is a problem called the vanishing gradient problem in this kind of models that can be solved by selecting specific activation functions. And if the neural network is classifying okay, but you are seeing that the error on your training data set is lower than the testing data set, you may have an overfitting problem. But if the error is high, both for your training and testing data set, you may have an underfitting problem. So if your model is underfitting, think about increasing the data, the training data, or making a more complex model by adding layers to your neural network. But if your model is overfitting, try to use regularization by penalizing a very complex model and to use dropout. For instance, to take some connections out of your neural network, or also doing pre-training or transfer gap. So that's all, and see you in the next video. Welcome to the course on how to process and extract features from audio files. We are going to start with a brief introduction on what is sound. It is important to know what are we measuring. So there are basically two definitions for sound. One is a physical definition where sound is defined as a vibration that propagates as an acoustic wave through a specific medium, which can be a gas like air, a liquid, or a solid. But if you want to do deep learning or any kind of machine learning application, for instance, to do sound tagging, you need to know that there is another definition for human perception of sound, which can be a little different from the physical definition. In human psychology or physiology, you deal with how the sound is represented in the brain. So you will be able to hear frequencies from 20 Hz to 20 kilohertz, and instead of measuring frequency directly, you will be hearing pitch in the sound, which is slightly different. We are going to see about it later in the course. So sound can be defined as an oscillation in air pressure, where you will have molecules of air, and when the molecules are close together, you will have higher pressure, and when they are further apart, you will have a lower pressure. So you can represent these differences in pressure as a wave. This is a sinusoidal signal, a periodic signal, and you can measure, for instance, in the x-axis, representation of the space, or also a representation of time in the x-axis. And in the y-axis, you can measure the pressure differences between each point of space. So let's do a brief recap on waves. Probably you've seen this kind of introduction at college, but it's good to refresh some concepts. For instance, that a wave has associated an amplitude, which is the distance between the equilibrium point, for instance 0, to the value of the measure in a specific point of time. For instance, this will be the amplitude, which is the maximum value that this periodic wave can attain. This distance will be the amplitude. So this is a sinusoidal waveform. We will have different phases of the wave. For instance, the phase at 90 degrees will be this amplitude. And when the signal repeats itself, you will form a period or a cycle. The amount of how many cycles do you have per second is the frequency. So you can have sinusoidal waveforms, but you can also have square waveform, rectangular waveform, triangular waveform, and so on, like sawtooth waveform. Each of those will have a period associated, which is the minimum unit of the signal, so which can be defined. Afterwards, you can have a signal with a lot of periods, but the basic unit of the signal, without repeating itself, will be the period. Okay, let's start by importing some libraries to begin our coding. We are installing the latest version of FastAI. And torch audio. This will be JIT. I have it already installed, so I can proceed. Let's import some basic libraries. Matplotlib for do some figures and some calculations. And now let's start loading some data. This is freely available data. Let's define the data folder. Just in case. And we are getting the data. So we can start playing one example. Let's begin with let's load an example. And in the notebook we are going to have this player.
And what about terms like over the limit?
And we can play it.
And what about terms like
here.
over the limit?
We can mute this if we
And
want.
what about terms like over the limit?
So the idea is that we are going to compare this library with another one which is a little bit more advanced. It is called Librosa, and the difference is that you have a lot of more options. For instance, you can define a sample rate. We can load the example that we just used. At this time we are not defining a sample rate. And we can obtain, for instance, the value in hertz of the sample rate, which is how many times do you measure a signal per second. So the idea is that if the sample rate is higher, you're going to have a better quality sound in the recorder. The sound file is a time series basically, so you can display how long is the time series, and you can also display the duration of the file, which basically is the length of the time series divided the sample rate. So we have that the sample rate of this audio file is 16,000 Hertz, that the amount of time points that you have in the time series is this amount, and you have this amount for the duration of the audio file.
And what about terms like over the limit?
Now, we can plot this signal to have an idea of the shape of the audio wave. And for that, we are going to import from Librosa display. We are going to create a figure, and we are defining its size. Let's check what happened here. This is fixed size. So we can see it here. We can see the audio file represented as a wave. We can see that it starts in about 500 milliseconds, and it lasts for the amount of time that we have here, 3.16 seconds. Okay, now that we have the audio file displayed, we can start analyzing some special quantities like the pitch of the sound. Okay, now let's define a function to create different tones using different frequencies. So let's define make tone, specific frequency. Let's define a length. And a sampling rate. Let's define the time axis. Is going to have a sinusoidal shape. Two times pi times the frequency times t, which is the time. And now let's create two clips, one of 500 Hz and the other of 1000 Hz. Okay, let's hear the first audio clip. Now with the second one. You can hear that it's a higher frequency. You can perceive it also as a higher pitch. We can see what happens if we decrease the sample rates. You can see that this sound is of a higher pitch, but if I just decrease it, dividing by 2 the sample rate is like having less samples of the sound that you are recording. So you are going to hear it as a 500 Hz audio file. Okay, let's see what is the shape of those audio files. So let's plot a figure. Okay, the idea is to be able to see 2 cycles of the signal. If we are using the 500 Hz file, that means that we have 500 cycles per second. And if we have a 16,000 sample rate, what we are going to have for one cycle is just dividing 16,000 by 500. That will give you 32 samples. So if you want to print 2 cycles, you define it as the double of 32. So it's 64, and this was missing. Now, as you can see, we have 2 cycles of this audio file. This is a sinusoidal shape. This will be 1 cycle and this will be 2 cycles. Okay, now we have been handling until now a measure of frequency, but what we perceive is different from what a machine does because of the way that the brain and the audition works in humans. So we can use a different kind of measure, which is the MEL scale, that it's based on how humans perceive sounds. So basic idea is that you will have some people and you will ask them to rate the tones, and afterwards you will feed a logarithmic function to try to replicate the sound perception. So for instance, if you have a frequency of 20 Hz, if you remember, we can perceive from 20 Hz up to 20,000 Hz. So a 20 Hz feature will be a zero of the MEL equivalent. So we can have this into account if we want to do a deep learning classification, because we want to be able to classify sounds as a human perceives them. So there is a more useful representation of sound called spectrograms, where we are going to be able to see the frequency instead of the amplitude of the signal. Okay, so what is the way that we perceive the amplitude of the audio files? You may be familiar with this concept, which is the decibel. The decibel is a way to represent how loud is a sound, and it's also based on a logarithmic scale. So the idea is that if you have an increase of 10x in the sound, for instance, if a sound is 10 times louder than another sound, you will have an increase on 10 decibels of the sound. So if you have a 20 dB louder sound, it means that it's 10 by 10 or 100 times louder that you are going to perceive. So this is a scale, just to have an idea on what are the measures. For instance, if you are hearing some moderate rainfall, you will hear about 40 decibels. But if you get higher and higher, there is a safety limit from which you will be at risk of developing hearing damage. So for instance, a chainsaw or a jackhammer in the street will be too loud and you will need to use some protection for your hearing. So let's plot a spectrogram. We are going to use the LA library. We are going to obtain the magnitude and the phase of the signal. Okay, what we can see here is a first approach for a graph displaying the spectrogram. So the idea is that you're going to have the duration of the audio file in the x-axis and the frequency, meaning that if you have this part of the graph that it's in a lighter color, that means that you have a sound with a specific frequency at that time of the audio file. Let's do some other plots. For instance, instead of using a spectrogram using the frequency, we are going to make a mel spectrogram, meaning that we are going to display the frequency as a human perceives it. So we are going to use the same sample rate. Now you can see that the scale is different. We can have a better resolution of the different frequencies if we are using the mel spectrogram rather than just the frequencies. Now let's make a better plot. We are going to have the time in the x-axis, and let's also plot a color bar to have a reference. Okay, we can see that this is much better. We can see that we have a very informative plot now about the same sound that we have been listening here. Is this one, is the Y sound.
And what about terms like over the limit?
We can see that if we just plot the time versus the amplitude, we don't have a good idea about the frequencies. We can see, for instance, that we have a high frequency sound, but you cannot define the exact frequency of each part of the audio file with this kind of representation. But if you use a spectrogram, you will have what are the frequencies that you will have at each point in time, but also you will have the loudness of that part of the frequency. For instance, you will have, if you don't have any kind of frequency, for instance, a high frequency in the first part of the audio, you will have a very low contribution. But if you have a very high contribution to the loudness of the sound, you will have a higher decibel measure for that part. regarding that part of the audio file in time and also the frequency for that part of the audio file. So you can also represent this as the energy of the wave, meaning that higher energy means a higher area under the curve of the signal. Technically, it's the area under the square magnitude of the considered signal. And you will have it as the y-axis. You are representing y as the amplitude of the signal and time as the x-axis. So we can extract a lot of parameters to use machine learning and try to do some audiophile tagging. For instance, you can obtain the minimum value of the signal, you can obtain the maximum value, or the mean. That will be the signal minimum, maximum, and mean. But if you want to use another kind of feature to do your classification, for instance, instead of looking at the amplitude of the signal, you will need to do a Fourier transform of the signal. Probably if you had some physics courses in your college years, you will remember the Fourier transform. But basically the idea is that you will extract the contributing frequencies of the signal using the Fourier transform. So the Fourier transform decomposes a function, in this case will be your audio signal, which is a function of time, into its constituent frequencies. So let's begin by defining some example files. We are beginning by loading the example. Just to.
And what about terms like over the limit?
Have an idea of what was the sound. Let's define a spectrogram for that sound with 1600 of sample rate. Sorry, 16,000. This will be a parameter for the Fourier transform. Another parameter for the Fourier transform. The resolution, the minimum frequency, and no maximum frequency. Minimum amplitude, maximum decibels, and let's display this new spectrogram. Let's define a maximum frequency and the label for the time. So what happened here? Now we have the spectrogram with our parameters. We set no maximum frequency. We set a specific resolution. And now let's make some tones. The idea will be, after creating the tones, to be able to see them by the Fourier transform. So we have a function to make the tone. Now let's define a function to add 3 tones. Okay, now we have an audio file with 3 frequencies. Let's display. Now we can see the signal and the sound, which is a combination of 3 different frequencies. The first frequency, the second, and the third. If you add a sinusoidal function with those frequencies, you will have this as an output. But now we want to extract those frequencies from the signal. So we will need to define the Fourier transform. We are going to use the SciPy fast Fourier transform. Defining the frequency and the plot. We can see that in this plot we have the 3 frequencies that makes up this signal. So this will be the decomposition into the fundamental frequencies of this signal. Okay, in this case we have a very well defined frequency profile, but what happens if we use an audio file like the one that we used at the beginning with the guy speaking? So let's load the example. We can see that there are a lot of frequencies contributing to the human sound, but most of the frequencies are located in the lower spectrum, from 0 to 1000 Hz. So the idea for machine learning will be to extract those kind of features and use it in your models. In the next video, we are going to begin coding a machine learning classification algorithm. Okay, now let's begin developing our model. Let's import the basic functions. Some library to upload the data. Let's look at our files. We can see the datasets of this Kaggle machine learning competition. And now let's define the path of the data. Okay, now let's locate the training data. And in case that we want to submit for prediction, Okay, next we are going to load some spectrograms. Okay, now let's read the datasets using pandas. And our test data. Let's concatenate. We want to train with curated data and noisy data. To train the neural network to handle noisy data too. And let's load it to the X train variable. Let's see what happened here. Okay, now we are going to import the libraries for the model. Okay, now let's import FastAI. We are importing the vision libraries because we are going to work with the spectrograms. Now let's define a function to open images. And we are going to standardize the image. Let's open those images. And do some preprocessing to show them. Let's see what happened here. Running it. Okay, the problem was here. Is run int, not run init. So we are loading the spectrograms right now. Meanwhile, we can continue. And when this is finished, we are going to be able to see some spectrograms. Meanwhile, we can code some other variables, like a score for a classification. We are going to use a ResNet, not pre-trained, but we are going to use the F-score as the metric. Okay, now we can see some spectrograms. We can see the spectrogram from clapping, foragon, raindrops, and so on. The idea will be to classify those sounds by tagging them. So let's run this part of the code. We can see that we are training the model. And we can see how the error goes down depending on your learning rate. There is an optimum learning rate for this kind of models, so we can take that into account. Okay, now let's continue with our coding. Let's see what happened here. We don't need this line. So because we already trained the model, we can delete the file so we can free some memory. And now let's look at the training, up to the test set. Let's load it. And a place to keep our predictions. Okay, there was a typo in the code. We can see that after fixing the code, we are going to have the training and the results of the validation. You can set how many epochs do you want. I set it to 100, but you can set it for more epochs if you want to have a better result. And you can see that the training loss, which is the error, and the validation loss gets lower and lower until you get a pretty good result with very little error. So that's all for this model. We are going to use another model in the next time. Okay, let's begin with a new model. This is going to be with the Keras library, and the neural network will be a little bit more complex. So let's start importing the libraries. Some basic functions. and matplotlib for some figures. We are going to import LibRosa. We have been doing some tests with LibRosa in the first video. NumPy for some calculations. Pandas to read the datasets. Model selection for splitting the training and testing data. Some augmentation of the data we are going to use. We are going to import Torch. A progress bar. The optimizer. Will be and some transforms from Torch Vision. Let's see what happened. Okay, this is import. Great. Let's define some content. Some pre-trained models. Let's define the number of epochs. And the batch size. Let's define the learning rate. You can change it if you want and see the effects on the neural network. How much we are going to wait in the case of a plateau. If we are going to use the curated data, it's a little bit more clean. If we want to use augmentation in the training data, the model type that you want, and a zero. If we want to use mix-up in the neural network, the activation function, we are going to use linear. The loss function is going to be VCA with logits. And let's define a function for setting the constants. Probably it will going to work too, but let's put it as it should be. Okay. Let's define some metrics for the classification. If there are some true cases, we treat the classes the rankings for the top scoring classes. This is num classes, and now the retrieve classes. The number of classes, if there is one with a true label, positive plus indices, number of hits for every truncated retrieval list, and calculate the precision. And we return the class indices. Let's define another metric. Let's check that everything is in order. The precisions. and the precision for samples by classes. The labels per class, the weights, and finally return the measures. Okay, let's import TensorFlow. To define a function to obtain the positive class predictions. Let's find the true labels. And put a rank on each element. Yes, that's what I had another parenthesis. Now, let's add and the retrieve class. Number of classes, I know that is a very long function, but it's very useful. Let's pick up the ranks. Let's generate the tensor. Find the positive position. Find the cumulative hits. Let's compute the precision. And finally, return. Okay, let's define the loss function. We want to import the backend. We're going to return the k-mean, meaning the mean from the backend, not the k-mean as for the method. Let's define the directory of the dataset. The directory of the preprocessed file. We are going to have the spectrograms here. And where is each of the files? We want to also train the model in noisy audio files. And to save our results, And what is the data files? Before was the CSV. And the test dataset. And the spectrograms. Okay, let's read the files now. In the case that we choose to use only curated data, let's check here. Okay, there was a typo. So now we can see the shape of the trained dataset. We can see each file is a .wav file, and we can see the labels. This is a bark, a raindrop, finger snapping, run, finger snapping, and so on. This is just the head of the dataset. Let's look at the test dataset. Now we can see that we have some .wav files, and the idea here is that we have a lot of labels, and we should put a number 1 on the prediction of the label. For instance, if I think that this is an accordion sound, I will put a 1 here. Okay, let's look at the labels. We are going to store it in a list. And we can see some of the labels here in this list. Let's define the Y of the train dataset, meaning the labels. We need another parenthesis here. So this is the shape of the Y dataset, meaning the labels of the train. We can see that we have 80 labels in total. We are loading the training data, the curated one, and if you don't want the curated data, we use the noisy data. If you want the noisy data to end. Let's check the length. So we have the length of the training dataset and the test dataset. Let's look this a little bit further. And we can see the shape of the tensors. Okay, now we can start the fun part, which is defining the model. For that, we are going to need to import several layers from Keras to start defining the neural network. Let's import everything. In regards of the layers, but for the models, let's import the sequential model. And some functions. Let's import the metrics. The ADAM optimizer. Let's import the inception layer. Version 3. Preprocess input. MobileNet. Exception. model. Okay, let's import some utils. Shuffle from scikit-learn. And finally, we are going to define the model. We are going to create an inception model. Number of classes as the output. The base model is inception number 3. A global average pooling layer. 2D. Remember that we are using 2D neural networks to analyze the spectrograms of the sound files. A global max pooling. We are going to concatenate the layers. A batch normalization. A dropout layer. You can change the parameters on the layers and see what happens with the results. We are going to store the predictions. And return model. Okay, we have the inception model now. Let's define the other models that we can try. We can try an exception model. Number of classes of the output as the output. The base model, the exception model, a global average pooling, global max pooling, a batch normalization layer, another batch normalization, let's store the predictions, let's create the mobile model, let's add a batch normalization, the ReLU as the activation function. And let's store the predictions. Let's see what happened here. Great. Let's define a simple block for convolution. The activation is going to be ReLU again. And return X. Let's define a simple convolutional neural network using those blocks. Let's add a flattened layer. A dropout layer. A batch normalization layer, a dropout layer, and let's store the predictions. And return the model. Okay, now that we have defined all the models, let's say that we want to use the mobile model. Let's check that this is chosen. We can look at the model summary. We can see all the layers here. The input layer, a zero padding, the convolutional neural network layer, patch normalization, activation, and so on. We have all the blocks and all. You can see that it's a very complex neural network. It's going to take a while to train. You can see that it has a lot of parameters, almost 3 million parameters, so it's going to take a while. And now let's start with some random seeds. Okay, now let's start training the model. For that, we need the validation and training datasets. Let's define a test size of 20%. And let's use the seed. Training generator. That was a markdown, probably. We are going to use augmentation. Let's use mixup. Validation generator. Let's define the training step. Depending of the length of the training set. And the batch size, the validation steps, let's cast it to int. Okay, we have this amount of training step, validation steps, and the length. We are using this loss function. And let's start with the compile of the model. the optimizer. It's Adam with the defined learning rate. Let's print our values. And we have our parameters here. Let's use the model fit. Okay, and the network started with the training. So afterwards, we are going to be able to evaluate and obtain our predictions. So see you later when this training is over. Okay, I decreased the number of epochs a little bit. So the idea is just to see how this is working. If you want to improve the accuracy by reducing the error of the classification, you can do it. You just have to wait a little bit more because it's a very complex neural network. So let's say that we want to see how this model is getting better during each epoch. So let's plot a figure. Okay, now we can see how the error gets lower and lower during each epoch for the training and the validation dataset, and also that the accuracy gets higher. So the idea is that if you increase the number of epochs, this result will be even better. So this is for the validation dataset. You can do the same to the testing dataset and obtain the values for your classification. If the categorical accuracy is not so good, just increase the number of epochs. And also you can try different neural network configuration, like changing the number of layers, changing the model. We use a mobile model, but you're going to have the code with all the models so you can change it and see how the model performs. So that's all for this video, and see you next time.